thank you very much for both of the introduction. In the few remaining minutes, from the 21st century. But I want to say that it's a very special honor for me to be giving the Chandrasekhar lectures because Spenta mentioned Chandrasekhar's 7 periods, and I would say his first period really marks, in the 30s, really marks the beginning of our conceptual understanding of what a black hole is. And then his last period on the mathematical theory of black holes is what our group at Harvard is working on now, and we hope that we have sort of added some substantial insight into what his work on black holes in the last period of his life, what it meant. So it's a wonderful thing for me to be giving these lectures. So during the 20th century, a lot of problems in all areas of physics were solved by turning them into the simplest of all, what was thought to be the simplest of all systems, the harmonic oscillator, which is a spring or a pendulum or a ball in a well. So the culmination of that, I suppose, is the standard model of physics, in which in perturbation theory we describe all the forces of nature in terms of a big zoo of harmonic oscillators, which are springs which are all attached to each other and interacting. We're all just one giant harmonic oscillator. That's sort of the view of 20th century, and other problems were transformed into harmonic oscillators and then solved. So the subject of this talk is that black holes are poised to play a similar role in the 21st century. It turns out that not everything can be turned into a harmonic oscillator. We need more tricks. And the reason that black holes are so interesting is because, as you just heard Spenta quoting Chandrasekhar, they're the simplest object in the physical universe, but they're also the most complex objects in the physical universe. And how is that possible? Well, according to Einstein's description, black holes are literally, they're not empty space, they're holes in space. So when you get to the horizon of a black hole, it's just a hole, there's nothing. So it's simpler than what we would usually think of as nothing, namely empty space. It's really absolute nothing. On the other hand, as began to become clear in the 70s, from the work of Carter, Bekenstein, Hawking, Christodoulou, many others, they're also, in a different sense, the most complex objects in the world, in that there's believed to be an upper bound into how much complexity you can cram into a region the size of a black hole. And a black hole, according to the work of Bekenstein and Hawking, saturates that upper bound. So they're both the most simple and the most complex. Now, in the last decade or two, we've understood, it seems very contradictory that something could be the most simple and the most complex, that simplicity and complexity are two sides of the same coin. But we've managed to understand that in starting out from string theory, but the understanding that we gained transcended its origin, and the way that the black holes are able to encode, be simple and complex both at once, is both conceptually and computationally powerful, and it's been applied in many different areas of mathematics and physics, some of which I will review later. So here's a cartoon of progress in physics. Whoops. So in the 20th century, when I got my PhD, my thesis advisor, thank God it wasn't Professor Jaffe. Who knows what he would have done? Would give me a problem and say, turn it into a harmonic oscillator. So he said, at that time everybody was working on this theory, the strong interactions, QCD, and he instructed me to beat up on QCD until it turned into a harmonic oscillator, and then he gave me a thesis. Now in the 21st century, I do a variant of the same thing. Depending on my mood, I give some problem to my students, I tell them to turn it into a black hole, and when they succeed in that, they get a thesis. So here's an outline of this talk. I'm going to give a biography of the black hole and what we've learned from it. I'll talk about some of the applications, including some of the recent things that we've done with the rotating black holes, taking up on Chandrasekhar's work. And then I'll talk, though I'm not really going to use string theory in the talk. String theory played an important role in understanding how things fit together, and I'll talk about that and the current status of string theory, and then I'll talk about what the future might hold. So here's the dramatic birth of the black hole. Einstein, after fumbling around for 8 years with all kinds of different theories of gravity, in November 25th, 1915, discovered the Einstein equation, and it said that he believed that the equations were so complicated nobody would ever find a solution. But 2 months later, Schwarzschild found the Schwarzschild solution, and Einstein announced it to the Prussian Academy of Science, and apparently Schwarzschild said, "It is always pleasant to have an exact solution in simple form at your disposal." I think truer words were never spoken. We've all been experiencing that pleasantness for 100 years now. Then, a few months later, he died on the Russian front. And here's Schwarzschild's formula, describing the so-called Schwarzschild solution to the Einstein equations. Now, he had it in completely explicit form, and despite the completely explicit nature of this solution, it was over half a century. Nobody had any idea what this meant. And it was over half a century before anybody understood it. And then a little bit after that, it was the quantum part was thrown in, and now we're all confused again. It's a half a century later, and we're still struggling with this formula. Though, of course, we know a lot more about it than we did. So so here's the history. So that was 1916. In the 30s, Chandrasekhar, but when the solution was written down, you see it has this funny region here when this variable r, which is the radius or the distance to the black hole, is equal to twice Newton's constant times the mass of the black hole. Things become this becomes infinite and that becomes zero, and nobody knew what that meant. And it was thought that you couldn't really, that there was something unphysical about it, that general relativity there wouldn't really ever be such things in the universe. But the first indication that this was not so was given by Chandrasekhar, and also Oppenheimer and Snyder a bit later, that if you have a star that's big enough, it collapses into a black hole. And just to indicate how confusing the whole subject was, the great man himself actually wrote a paper saying they were wrong and that you could never get a black hole. But still, it wasn't until the 50s that Finkelstein and Kruskal understood that this surface of the black hole is like a one-way membrane. a horizon. That this surface where this special radius is a radius that you can cross from the outside to go in, but you can't go from the inside to go out. Now, another amazing thing, the equations were sitting there for 50 years. Now, the real black holes up in the sky are not described by the Schwarzschild solution because they're spinning around. And it was understood, again, very early on that there should be some kind of spinning solution, but finding the solution, even though it was a well-posed graduate student, well-posed problem which would have gotten any grad, sitting there, it took 50 years to find the solution. Why Kerr didn't get a Nobel Prize for this, I don't know. But so that solution was discovered 50 years later, which we're going to talk about. Then in the 60s, sort of the modern story, Penrose, Hawking, and Carter understood, and Wheeler invented the name black hole, really began to understand what happens to space-time, how space-time gets warped and twisted, and how your notion of causality changes around a black hole. That was understood in the 60s. Then in the 70s, in the early 70s, two things happened. First of all, in the 60s, people might have still been saying they didn't believe in black holes. But in the 70s, they began to see things up in the sky, including Cygnus X1, which by now we're pretty sure Cygnus X1 is a black hole. There are other things that we're completely sure are black holes. So at that time, people began to see them up in the sky. And in fact, we now believe that it's very clear that we are, at this very moment, our entire solar system, the galaxy, is rotating around a huge black hole in the center of the galaxy that's 4 million solar masses. So this was 60 years after Schwarzschild's discovery. And at the same time, the classical structure of a black hole, theoretical advances, which of course were needed to interpret the observations, began to reach a really nice stage of maturity. And they were summarized by the so-called laws of black hole mechanics. And there's the first law of black hole mechanics, which relates, and they were similar to the laws of thermodynamics. So here's the first law of thermodynamics. So the first law of thermodynamics says that if you take the temperature of the system and you multiply it in any process by the change in its entropy, which is a measure of the disorder of the system, that's equal to the change in its energy. And then if there are other quantities around, the charge or angular momentum, there'll be corrections to this first law. And it was realized that, so these laws were discovered by doing measurements on fluids and gases and so on, and measuring their properties when you heat them up. But then we had these laws of black hole dynamics, which tell you that if you take the strength of the gravitational field at the horizon of the black hole, that's called the surface gravity, and multiply it by change in the area of the black hole, that's equal to the change in the energy plus corrections. And these two laws look very similar if you just interchange entropy with area and temperature with surface gravity. Then the analogy got better when it was realized that the second law of thermodynamics says that the entropy always increases, whereas the second law of black hole dynamics says that the area always increases. That is, classical black holes only grow in size. And again, if we interchange entropy or area with area, these laws go into one another. Now, roughly speaking, it's not nearly so simple when you try to make it precise. But roughly speaking, it's fair to think that the area of a black hole always increases because things can go in, but they can't come out, and when they go in, the black hole gets bigger. Now, entropy was observed already in the 18th century to always be increasing, but Boltzmann explained it as a result of his interpretation of entropy as a measure of molecular disorder. So everybody knows that that disorder always has a tendency to increase. So if you straighten up your apartment, and then you go in and you do a few things, you cook dinner, you get some books, and you go out, it's going to be more disordered than before you arrived. So in general, every process will tend to increase disorder. Now, the amazing thing is that these are really, they sound wildly different, but the fact that a black hole always increases in area and the fact that disorder always increases are exactly the same phenomena in disguise. And these two descriptions of this phenomena are related in the same way that the simple description of a black hole and the complex description of a black hole are related. So then how did we get to understanding this? Well, Hawking in 1974 famously discovered that black holes, in fact, when you include quantum mechanics, are no longer completely black. The laws of the quantum uncertainty principle allows light to sneak out of the black hole, and it comes out with a temperature which is exactly equal to the surface gravity, and that's consistent with the black hole having an entropy which is equal to a quarter of the area of the event horizon. And now what we have is no longer separate laws of black hole mechanics and thermodynamics, but we have combined laws. So we have only one law, the so-called Generalized Law of Thermodynamics, which says, for example, that the entropy outside of a black hole plus the area of the event horizon always increases. So, when you take into account quantum mechanics, the area of the black hole need not always increase because the light sneaks out and the black hole shrinks. But the light comes out in a very disordered fashion, and so the total entropy is increasing. Similarly, if you take a cup of coffee, which has a lot of entropy, it disappears, you throw it in a black hole, it disappears from the observable universe, so is no longer part of the disorder in the observable universe, but the black hole gets bigger, and so we have less information because the black hole has grown and occupied more of space-time. More of space-time has become inaccessible to us. So it's, of course, a very unsatisfactory state of affairs to have two descriptions of a phenomena, two ways of describing a phenomena and not being able to make them understand why they're the same. And so what we need is to understand the black hole entropy in a precise way as a measure of the disorder of a black hole, that is, according to the theory of statistical mechanics, as the logarithm of the number of possible microstates that a black hole can that a black hole can be in. So this is a central challenge, one of the important problems in modern physics, to understand this. And since it involves both gravity and quantum mechanics, we have to have a quantum theory of gravity, and those have been in short supply. So, now 20 years later, so when string theory came along, which is a proposed quantum theory of gravity, it seemed natural to ask whether string theory could explain this, whether this number could be computed out of string theory. And this was accomplished 20 years later for certain black holes which are not quite the black holes that we see in the sky. They're in 5 dimensions, and they have a special property called supersymmetry, and they carry charges. Nevertheless, they have an entropy in the same sense as the astrophysical black holes, and we were able to use string theory to understand that entropy, get a more detailed description of this hole in space in terms of all the constituents, and perfect agreement was obtained, and this was the first example in string theory of what's now known as the ADS-CFT correspondence. And this whole construction shed a lot of light and led to a lot of developments in string theory. That's partially what I discussed at the Homi Bhabha lecture, which I gave 5 years ago. But that's a different lecture. That's not the lecture I'm giving today. I'm talking about black holes. Now, when this calculation was done, it was a very long calculation. It involved all kinds of factors and some advanced mathematics, algebraic geometry, and so on. And it wasn't until the last minute, when all the factors, every last thing was tidied up and sorted out, that this agreement was found. And the calculation gave the illusion that it depended on all the precise details of string theory. But in fact, it was understood a year later that that was really just an illusion, that the answer was guaranteed to come out correctly, and it was guaranteed just from, if you boiled it down to its key ingredients, it was guaranteed to work out just using some arguments that are just consistency arguments, that you have a consistent quantum theory of gravity and it's unitary and has a few nice properties. And this is really what should have happened. This is really what we should have expected to happen. And let's go back to understand why it would have been very surprising if you had a universal law, like the aerial law for black hole thermodynamics, and it depended on microscopic details of things that were too small to see or measure. So let's go back to what Boltzmann did. So Boltzmann, in the 18th century, people knew the laws of thermodynamics. They'd measured them. And Boltzmann explained those laws, the first and the second law, from statistical reasoning on about fluids and gases, but he had to assume that gases and fluids were not continuous media. Because if they were continuous, you would have an ultraviolet catastrophe, and there would be infinitely many degrees of freedom. So he had to assume the theory of molecules, which at that time was controversial, but he didn't need the whole periodic table. So he didn't really need all the details of what molecules were. He didn't even need to know how big they were. He just needed to know that gases and fluids are not infinitely smooth things, that there's a smallest unit. Now, quantum gravity has a similar ultraviolet catastrophe, and we need to understand black hole entropy. We have to assume some consistent completion, that there's some kind of cutoff there, maybe similar to molecules, but the role that molecules played here was played by strings here, but we didn't really need, it doesn't really require on any details of the cutoff. So what was done for string theory was a little bit as if one first computed the periodic table and then looked at properties of all these things in the periodic table and find that they obeyed some universal law, which were the laws of thermodynamics. You can throw out the periodic table, and that was what was done for these kinds of black holes just a year or two later. Okay. Now, that still didn't get us to the kind of black holes that we see in the sky, but just in this last year or two, we've been able to abstract this reasoning and apply it to, one assumes that there's some consistent quantum theory of gravity, and we've been able to abstract the reasoning that we use so successfully in string theory to not all the black holes we see in the sky, but a class of them. And the class is the so-called extreme Kerr black holes, and those are ones whose horizons rotate nearly at the speed of light. So let me discuss those. So a Kerr black hole is just a rotating one, and it has angular momentum. There's an upper bound on how fast a black hole can spin around, and the bound is given by the angular momentum is equal to Newton's constant times the square of the mass. These things don't have a temperature, but they do have a Bekenstein-Hawking entropy, which is just equal to 2 pi times the angular momentum in Planck units. Now, this ratio of the angular momentum to g over m squared turns out to be astronomically rather easy to measure, easier than the mass, surprisingly. And the most observed black hole in the sky, GRS 1915 plus 105, has its mass is only known to about a factor of 2, but it's known that it's very near extreme, which is what we want, because it's only the extreme ones that we've succeeded in understanding. Now, hopefully, we'll understand all of them at some point, but now we'll take what we can get and we understand the extreme ones. So this one is known to be, this parameter is known to be within 2% of unity. It might be much closer. They just can't measure it that accurately. There's also some of the big monster black holes in the middle of galaxies that are known. Last year, a paper appeared that in one of the Seyfert galaxies that there's one that's rotating at 99% of extremality. So here's an artist's rendition of GRS 1915 plus 105. The black hole itself is right there. There's a companion star, and matter is pulled off the companion star. And this I got off the NASA website, which has all kinds of wonderful graphics. The matter is pulled off the companion star. It gets into what's called an accretion disk. It spirals in, and as it spirals in, it heats up because it loses energy, and it radiates black body radiation. And this radiation has been very carefully measured and compared with the theoretical simulations. And that's how they figure out how fast this thing must be spinning. Now, the interesting part here, the black hole is right in here. This is jets coming out of the poles. The interesting region where life becomes simple is right in the middle here, right at the edge of this accretion disk, where everything is moving, as I'll explain in a minute, at the speed of light. And some very special things happen there that enable us to say much more, to go beyond what we've usually been able to do, and to have some understanding of the entropy of this black hole. Now, what we want to do, it's a familiar idea in condensed matter physics, that we want to understand some complicated system. You can't keep track of all the variables, so you go to some limit where things simplify. And the standard limit in condensed matter physics is a low energy limit, or a long distance limit, where you ignore things which are very short, and you just look at long wavelengths, which is the same as low energies. Here we're going to consider also a scaling limit of this type, but instead of going to low energies, we're going to scale to small radii right near the horizon of the black hole. And in fact, they're not very different, because as you get to small radii, the energies become highly redshifted. So the small radius limit is also a low energy limit. Now, NASA has kindly provided us with a video So, okay, there we go. So this is a video of GRS 1915, and this is the accretion disk. And what we're doing here in this video, which is exactly what we want to do in our calculations, is to zoom into this region right at the boundary of the edge of that hole. And we'll find out that there's some dramatic simplifications that occur there. So what happens in a black hole? So if that video camera at the back of the room were a spinning black hole, in order to stay where I am, if we're spinning this way, it would try to drag me around and I'd have to walk slowly in this direction. And as I got nearer the black hole, I would have to walk faster and faster in the other direction just to stay in the same place. And then there's a region called the ergosphere, which is still far outside the horizon of the black hole, where even if I run at the speed of light, I would get dragged around the black hole. Then when I get to the horizon of the black hole, and if it's an extreme black hole, I'm pinned to the horizon and I'm forced to move around. All excitations are forced to move around the black hole at the speed of light. And I can't in this lecture describe the mathematics, but this is the reason why things are so simple when you get to this region, is that everything has to move at the speed of light, and it's very hard to go at the speed of light, and there are many fewer possibilities if everything is dictated to go at the speed of light, and so we can use consistency requirements of what has to happen when things move at the speed of light become much more powerful. And the other thing we can see already from this picture is that the physics of what we have to describe has only one space, one time dimension. That is, it's two-dimensional. There's time, but everything is constrained to just be moving in this one direction around the black hole. And so a four-dimensional problem collapses into a two-dimensional problem, and we all know that two-dimensional problems are far simpler. So it turns out that the two-dimensional problem that arises is the simplest and the most beautiful and the most mathematically constrained of all two-dimensional problems. And that is, it's the problem, it becomes equivalent to a problem of a two-dimensional conformal field theory. There's a Virasoro algebra. It has characterized by central charge. And we can compute that central charge, and it's just given by 12 times the angular momentum in Planck units. And there's also a temperature. And all of this follows just from consistency of quantum gravity and a careful analysis of the property of the symmetries of Einstein equation.
I have a question.
Yes.
When you say quantum gravity, do you simply mean four-dimensional quantum general relativity?
I mean any theory that includes Einstein gravity and quantum mechanics. I don't need to know it sounds like we're getting something for free, but it's true. I don't need to know the details. Of course, people have been spending, including myself, and it's a wonderful and interesting enterprise, trying to understand the details of how quantum mechanics and gravity can fit together in one theory. But for this purposes, we don't need to know those details. We just need to know that it can be done consistently. And that's as it should be, because it would be very surprising that in order to understand the behavior of an object which is, like a galactic black hole, which is, 4 million miles across, that we would need to know something at distances unimaginably shorter than a centimeter. That would just make no sense. And indeed, we don't need that. We just need to assume that somehow nature knows what to do when it gets to those short distance scales. And now, when you have a two-dimensional conformal field theory, and it's a good one, in other words, it's so-called unitary and energy is positive and so on, as it should be, because there's black holes and because the world is good, and these things really exist, you can actually reproduce this formula for the entropy. So we can understand, so we can actually count the microstates by rephrasing by describing the black hole in terms of this conformal field theory, and it doesn't depend on the microstates. Now, even better, I guess this isn't very visible here, but that's not all we can do. Every property, so there's a duality. It's this simple explanation and the complex explanation. The complex explanation is the conformal field theory. There are many, the black hole has these many states that give the entropy. But in principle, everything can be calculated from either picture. And one of the things that we have done, this is a paper by Chandrasekhar, it's sort of the culmination. He wrote a beautiful series of papers in the 70s where he solved the Dirac equation and computed the scattering of fermions off a rotating black hole. And they're very complex formulas, which I think you probably can't even see. The resolution isn't good enough. But take it from me, they're very complicated formulas. And if you look at these formulas in the right way, we showed that they are precisely the formulas of correlation functions in a two-dimensional conformal field theory. So it's a new lens on an old story. So this kind of situation, this kind of holographic duality, where you have two descriptions of the same object, is a recurrent theme in modern physics. So it's, on the one side, it's simple, complex, black hole, a thing with a lot of disorder, thermodynamics, statistical mechanics, gravity, quantum field theory. It's called holographic because it's reminiscent of the way that a simple-looking image can be encoded in a very complicated way on a holographic plate. Now, I think I've only written down one equation in this so far, and I've said a lot of words and so on, but don't be fooled by that. There's some very hard mathematics behind all of this, and this insight is not only conceptually illuminating about the nature of many physical systems, but it's computationally very effective. In other words, when we understand this, there are many things that we can compute that we weren't able to compute before. And so let me give some examples. So in nuclear physics, if you collide heavy ions, as they've done in Brookhaven, at high energies, they interact in some very complicated way that was very mysterious, and the behavior of the complicated mess that they formed was hard to understand. And it was finally understood by realizing that it actually could be viewed as a black hole. So in a sense, black holes have been made. It's a black hole in the dual description of the QCD, of the strong interactions that are occurring at this collision site. And so, very surprising to run into black holes in problems like this, but there it is. It occurs, there have been many applications in hard mathematics. There's something called the Gromov-Witten invariance, which there are whole conferences on in the mathematics world. And then there's something called the Donaldson-Thomas invariance, which there are also whole conferences on in the mathematics world. And it turns out that by looking at this duality, you can beat these things up and turn this one into this one. And now there are conferences talking about how these two, learning how string theory sorted this out. Now the conferences are joined together, and it's led to a lot of interesting developments, the wall crossing formulas, and so on. It's an important field in modern mathematics. One of the central problems in condensed matter physics, understanding high temperature superconductivity, has been argued, or people are trying to understand it in this way. And there's been a qualitative explanation of the anomalously high Nernst effect in some high TC cuprates, and there's been some experimental predictions, and it's also been applied to graphene, and there's now many conferences understanding how this works. They're not yet joined up with the people in the math conferences, but maybe we'll see. Okay, now one of the things that I find very exciting is the applications to fluid mechanics, which aren't really there yet, but seems to be starting, and it's a very exciting development whose modern incarnation really began here at TIFR. So it's been clear since the 70s, work of these people, that if you poke a liquid, you make waves in the liquid which are governed by the Navier-Stokes equation. On the other hand, if you poke a black hole, you make waves on the horizon, and they seem to be governed by the same equation. Now, I can't explain now exactly what it is that isn't understood about this, but there's some things that are very mysterious about it. Some aspects of this we haven't understood. But it looks quite plausible, at least to me, that these two equations, so these are possibly the two most important equations in physics. This one has been around for, 200 or 300 years. This is one that's been around for 100 years. And the amazing thing is that right under our noses we thought we were studying two things, but it's possible that they're the same thing. And in one corner of the solution space of these equations, precisely that statement was shown to be true by this group at TIFR. And if this can be understood, this might lead to a new approach to old problems over here, such as turbulence. Okay, so there are more examples where black holes are appearing where you wouldn't expect them. And there will certainly be more. But I want to use my remaining few minutes to say something about the role of string theory, which I haven't really discussed so far. So I'm just going to give a summary of kind of the current status of string theory. So string theory was discovered in the 70s. I mean, you could trace it back earlier, but it was discovered in the 70s as the apparently still unique solution to the deep problem of reconciling quantum mechanics with general relativity. Then in the 80s, it was discovered that not only did it solve the problem of reconciled quantum mechanics and general relativity, but it was in principle capable of also unifying all the forces and particles of nature. And it's the only example of a theory which can do either of these things. So over the last 3 or 4 decades, the subject has grown into a large and highly cohesive framework which incorporates nearly all ingredients of beyond the standard model physics. So what happens is, there has to be some new kind of quantum structure, mathematics, or so on that takes us beyond the standard model. And it might have happened that there were a number of competing proposals for such structures. But there aren't competing proposals. There's only one proposal. There have been some competitors proposed, most famously 11-dimensional supergravity, and all the competitors were found in the end. It was a very funny situation in the sort of in the mid to late 80s, where there was, the supergravity people thought they were better than the string theory people, and the string theory people thought they were better than the supergravity people. And then it was understood that they were actually describing exactly the same thing, just using a different language. It didn't have to be this way, but that's how it is. Right. Okay. So here's a kind of flow chart of views on string theory. So one view on string theory, so there's a lot of crazy discussion about how we should think about string theory. And there seem to be two main views. One is that string theory is everything. We're done. We've got it. We know all the laws of nature. And we're going to test. We're going to explain everything, and it will solve all problems and cure cancer. And if you take this point of view, you'll say, okay, let's make a prediction with string theory, and then you're led to you can't because there's too many, and then you start talking about the landscape, and then you find that's too hard, and then you give up, you go home and you watch TV. Now, a faster way to get there is the opposite point of view. That string theory is a bunch of mathematical nonsense, and everybody's just, making up problems for other people that, we're just, and there's nothing happening, and then so that gets you straight to the TV set, okay? Now I'm going to propose a radical point of view. String theory is not everything, it's not nothing, it's something. And we've solved some problems, and we haven't solved other ones. And that's just how it is. And if you take this point of view, you don't have to go home. There are a lot of fun things to do, and there are a lot of things. There's some problems that we don't know how to make progress on, and there's other problems that we do know how to make progress on. And it might be that, okay, so here's the report card. Now, the interesting thing about this report card, so the string theory is everything community would demand all A's. And the string theory of nothing community would say everything was an F. Now, I think we'll find that if you talk to people with any kind of vague understanding of the field, there isn't going to be a lot of difference on this report card. Maybe this one would be the most controversial, where I gave it an F. Some people might give it a B. I don't think anybody would give it an A. And there isn't going to be a lot of disagreement about this report card. What people will disagree about whether the student should be given up on or not, whether this is a hopeless case. Now, in contemplating whether the student should be kicked out of school for this report card, one should remember that it's the only student in the class. So if you kick the student out, you have to close the school down. So, okay, what's the first one here? Well, string theory, you might think I'm joking about this, that string theory is not ruled out as a theory of nature. But I'm dead serious. There is nothing else which passes this criterion. There is no other proposal which we can't rule out as a theory of nature. Perhaps there are things which might be called hopes for a proposal or something like that. And the world is a very particular place. And I remind you that from 1972, when string theory first came out, until 1985, when as Shiraz mentioned, we've found that there might be some phenomenological versions. In that 12-year time scale, it was believed that string theory solved the problem of quantum gravity, but was ruled out as a theory of nature because it couldn't produce a quark or an electron. And so it's very hard to write something down that can't be ruled out. And I think that's really the most compelling thing about string theories, that people would really like to rule it out, but they can't. Making an unambiguous testable prediction, I don't think we're anywhere near it. Now, there's a difference between making a prediction and, it could be that you didn't make a sharp prediction, but you saw some strings when you turned on the LHC. So things that you could see that would rule in string theory, there's some potential for that, and there are many people very optimistic about this. Maybe some people would move it into the B column. I don't think there's anybody on Earth that would give it an A. Solving black hole puzzles, I think we've done very well. Applications to pure mathematics have been quite extraordinary. Applications to physics, which we're beginning to see, I think it's doing pretty well, and I'm imagining that in the next decade this will move into the A column. An example of a unified theory, again, it's the only theory which has a symmetry which could unify all the particles and forces of nature. Uniqueness, it's not very unique. Well, there's only one string theory, but it has many phases, so it ends up being the same as if it weren't unique. Not too much to say about the cosmological constant problem. Hasn't had much to say about the Big Bang. And of course, it gets an A for solving this problem of Pauli's problem of the mathematical incompatibility of quantum mechanics and general relativity, which is where it all started. Now, there are many things to think about to go forward. We don't understand we've only understood a few little corners of all the possible black hole things. Somehow, we still haven't conceptually understood why entropy becomes area. And that's obviously very central. Our own universe has a horizon which is more like a de Sitter horizon, and we'd like to understand that. It has similar thermodynamics. There's the information puzzle. And I think that, we got to where we are now in large part by trying to understand these physical puzzles, and there's plenty of them left. And I think that we will see that what we've understood so far is just the tip of an iceberg of some really wonderful physical, mathematical structure. And so to summarize, we don't have a roadmap to the laws of, to understanding all the fundamental laws of nature. But what we can do is we can see around the next bend. And it's pretty clear that we're going forward, but we don't know exactly how we'll get to the end, if ever. Let me stop there.
Take some questions.
Yes, of course.
In one of your slides, when you mentioned gravity field theory duality, you had a line there. What statement do you expect to be able to make, say, as of today or in the future? Can we quantify that a bit?
Sorry.
You had this one.
This one?
No, next.
Oh, I'm sorry. Which one was it?
You had a list of dualities,
Oh, that one.
Yeah, here.
Yeah.
So, the second or third, and gravity to quantum field
Yeah.
mapping.
Yeah.
I would like to hear a little bit more about what you have in mind.
Well, that's one of our great successes.
Yeah, is it limited to ADS, or you want to be? You think one can make a more?
No, it's not limited to ADS. We've understood it concretely in some examples where it's not ADS. And I remind you that the whole beginnings of it had to do with black holes, the fluids and the horizons and so on back in the entropy and so on. And so the ADS is sort of a crutch that enables us a crutch which enables us to do some calculations. But already we've been able to do concrete calculations in contexts where we don't have ADS. But we still don't even quite know the frame. It's clear that there is a more general framework, but we don't really understand what it is. And I think this is an example of some very concrete thing that we're able to think about now and probably going to see progress in this.
Just a quick follow-up. So in 4D space-time, can you take a semi-classical black hole microstate and map it to a state of a quantum field theory one-to-one?
You mean like in an astrophysical black hole?
No. Take a large black hole with mass much greater.
What kind of? There's some examples of some unphysical situations that we can describe mathematically using string theory, and then we could answer your question in more precision than you could stand to listen to. Now, for a real black hole, like the Kerr ones I'm describing, we don't know, and we shouldn't expect to know the detailed description of all the microstates, because that will clearly depend on laws of physics that we haven't yet. It will depend on the laws of physics we haven't yet discovered. It will depend on what we see at the LHC. It will, so we wouldn't expect to be able to answer that question now, and we aren't able to answer that. We don't know how to answer that question now. The question that we do know how to answer now is why this dual quantum field theory has a density of states always must have a density of states that will map into the area. In other words, we've mapped the universal behavior of the Bekenstein-Hawking areal law to, we've identified it with the universal behavior of the quantum field theory that is the dual description of the black hole. But we couldn't give you a detailed enumeration of all the states.
In the applications of conformal field theory to condensed matter,
yes,
one can, for example, take something like a polymer which undergoes some phase transition.
yes,
Then one finds that the full free energy can be broken into a singular and non-singular part. And the behavior of the singular part is well governed by some central charge for the problem. But that has nothing to say about the non-singular part of the free energy. Now, in this black hole problem, you know the central charge, but maybe the entropy has other contributions which one is not taking care of, or what exactly is the meaning?
those would be subleading. Those would tend to be, in the context that we're in here, the pieces that aren't universal would be subleading. So, not every property of a conformal field theory is universal. And the properties of the conformal field theory that are universal, but there are many properties of a conformal field theory that are universal, but not every property. And it's exactly the ones that are universal that we've been able to, for example, the formula, Chandrasekhar's formula that I flashed up, which I'm sure nobody could read, for the scattering off a black, that turns out to be related. The form of that turns out to be related to a universal form of a correlation that correlation functions take in conformal field theory. And so when you understand how the dictionary goes between the black hole and the conformal field theory, you can read all that off.
What do you mean by subleading? I mean, in what kind of parameters?
The mass of the black hole. So the area law, if the Bekenstein-Hawking formula, of course, the entropy can't be the area because it's not dimensionless, right? So it's the area divided by Newton's constant times Planck's constant. And that's a very big number for an astrophysical black hole. What would it be? Of order 10 to the 50, or, it's huge. And so that has a subleading correction, which would be, I guess, of order 1. Or maybe it's the square root of 10. Anyway, it's small. There's a subleading correction. Subleading in the size in Planck units, basically.
In your work on the curved black hole, did you need supersymmetry?
No. Didn't need supersymmetry, didn't need string theory. It applies to the things we see in the sky.